Thank you everyone for joining. We will start now the Ionic Wireless workshop. My name is Amit Garay. I'm a business development manager in Tigo, and with me today is Daniel. Daniel is the VP Customer Success and Professional Services. So thank you very much for joining the workshop. We're excited to show you the Ionic Wireless Evaluation Kit made by Tigo. Tigo was founded with the vision of unbinding the industrial space by providing wireless mission-critical solutions designed specifically for factory automation. Ionic Wireless was designed to bridge the gap and provide a standard wireless communication fitting the harsh demands of motion control, rotating components, and retrofitting. Today, we will present Ionic Wireless benefits and practical use of Ionic Wireless Evaluation Kit. Today's workshop will be approximately a 40-minute session, during which we will go over an Ionic Wireless kit, show a demo, and some selected case studies. This will be a technical-oriented workshop, so feel free to ask questions using the chat. The questions we won't have time to answer live will be answered by a following email. Today's workshop is focused on presenting the Ionic Wireless Evaluation Kit. We will discuss Ionic Wireless application and benefits. Then we will show the Ionic Wireless Evaluation Kit components, know how to power up the setup, and set up variety of devices with Ionic Wireless. Eventually, we will go over the master's connection to both a PLC and to Tigo's software package named Tigo Engine. We will demonstrate how to configure the devices, how to monitor them, how to control the data, both process data and the on-demand data, or cyclic and acyclic Ionic parameters. Later on, we will present real case studies where Ionic Wireless was implemented and discuss its values and benefits. It is actually a good starting point for companies which already received their evaluation kits, or for people who are interested in Ionic Wireless solutions and would like to learn more about it. So I assume that most of you are familiar with Ionic or working in companies that offer Ionic products. Ionic Wireless is basically an extension of the Ionic standard, and it is designed to provide cable-grade wireless connectivity. It was designed based on key pillars. First, low latency of 5 milliseconds, reliability of 10 by -9 package error rate, which is 6 orders of magnitude more than any other wireless communication, or in even simpler words, it's 1,000,000 times more reliable than other wireless communications such as Wi-Fi, Bluetooth, Zigbee, and others. Furthermore, it offers scalability to support hundreds of devices in a single machine area or work cell area. And we'll even show you some examples of such applications later on. That is pretty much cable-grade reliability, but with actually better scalability. And moreover, Ionic Wireless is a deterministic protocol. This allows factory automation to sync clocks and rely on Ionic Wireless for mission-critical and high-performance applications. So eventually, to sum it up, Ionic Wireless enables access at the lowest level of automation on the machine with seamless and vendor-agnostic cable-free communication with sensors and actuators. So not just real-time monitoring like other wireless protocols that we know, this is about real-time control wirelessly on fast-moving machines. Ionic Wireless is used by many industry leaders. Those industry leaders developed a wide range of solutions. Each application was designed based on its unique requirements, and therefore there are applications such as rotating components like lathe, CNC, milling, and grinding machines, where the data is being collected from a rotating component. Motion control and transport track systems designed to increase machine capacity and flexibility. IIoT or retrofit of existing and new sensors on machine for predictive maintenance applications. Cobots and robots and effectors to allow better flexibility and reduce deployment complexity. So when showing those applications, the question that usually comes in mind is, what about power? And it is nice to speak about wireless, but where do we get the power from? Well, each application uses a different kind of power supply. Retrofit machines and predictive maintenance applications using usually the 24 volts power supply located on the machine itself. Cobots and robots are using power through slip rings. Transport track systems are using inductive power to transfer power wirelessly, and rotating components, push buttons, and remote controls are powered by battery. So following the live demonstration, as much as the time allows us, we will show selected case studies, but first, let's introduce IO-Link Wireless products and the IO-Link Wireless kit. So factory automation relies on 3 layers of technology. On the device layer, the bottom layer, every IO-Link device can be converted to IO-Link Wireless using off-the-shelf Tigo Bridge and closed IP67 product. Actually, moreover, industrial equipment manufacturers who like to develop their own IO-Link Wireless components may use Tigo Bridge and Tigo Air system-on-modules to integrate in their own devices. They can be integrated into rotating components, transport track systems, shuttles, cobots and effectors, and basically any digital or analog or IO-Link device. Then if we go 1 layer up on the control layer, an IP67 and closed Tigo Master 2TH is used for control and monitoring the data from the sensors, or one may use an integrated IO-Link Wireless system on module to implement in their own gateway or a master. Those masters on the topper layer, which is the software layer, can be connected both to a PLC and the Tigo engine software to configure the devices and to communicate the data. So now let's talk about IO-Link Wireless Evaluation Kit. The evaluation kit named TigoStarter K21. It is a basic setup that enables connection of a variety of sensors to PLC and to the Tigo engine. This kit includes a couple of Tigo bridges to connect IO-Link devices and also a single IO-Link hub to connect analog and digital sensors. It includes also 1 IP67 enclosed Tigo Master 2TH with OPC UA and Profinet or Ethernet IP support. It includes a single Tigo engine evaluation license, and IO-Link Wireless master and devices can be configured both from a PLC or Tigo engine. However, the Tigo engine allows a friendlier user interface and additional advanced features. This kit includes technical support from Tigo's wireless experts. The kit also includes all required cables for an easy startup. And Daniel, of course, is leading Tigo's support. So once you have the kit, feel free to contact him for support. Daniel, the stage is yours. Go ahead and show us how it's done live.
Hello, everyone. Thanks, Amit, for the great intro. In the next couple of minutes, we will go over the details and start showing the kits, the components, out-of-the-box experience with the kit, using the Tigo engine software configuration tool, and also connection with the PLC. In this diagram, we're showing the topology of connecting all the devices and the components coming from the kit. What you can see on the field devices are the hub and the bridges connected as devices connected to the Tigo master. And the first section of this introduction for the kit, we will go over and see the components and the connectivity, how we connect all those components and power up the system. When you open up the kit for the first time, you will see on the left the Tigo Master 2TH, 2 Tigo Bridge, which act as devices. Also brackets included if you want to mount those for more stability. An IO-Link hub, which is used to connect more sensors and actuators and all the required cables to power up and to connect the system. You should also take a look into the brochure, which explains about each one of the components and the cables which are coming with the kit. Let's see how everything is connected. First, we'll start with the master, the 2TH. Cables, L-coded power cables, two cables, one for the 2TH master, the other for the hub. And the decoded communication cable, which goes directly to the PLC or PC Tigo engine, connected at the top of the Tigo master. You will see all the blinking lights when powering up. All the components are powered, as Amit mentioned, connected to a 24-volt supply. Next, the second decoded, L-coded power cable connected into the hub. You can see the hub powering up. Now we'll connect the Tigo bridge to add the IO-Link wireless functionality into this IO-Link hub. Two A-coded cables supplied with the kit for the two Tigo bridges. One side of the cable is connected to the M12 connector, and the other is connected directly to the hub. The second bridge will be connected to an IO-Link vibration sensor. And this is it. You're up and running. The next stage will be to connect the software. See how we configure that with our own Tigo engine configuration tool. Two more steps that we're gonna cover in this presentation. The first, the Tigo engine, and the second will go over the PLC. The Tigo engine, as Amit mentioned, is a software-based engineering tool that we're providing as a license with our kit. You will get an executable to run on your computer and to be able to connect and configure those devices. Tigo engine is targeted to be an engineering, easy to use, intuitive user interface to help and ease the deployment and the configuration of the kit components. So let's see how everything plays out. In this example, we will connect those components, and we'll start by opening the web browser. It's a web browser-based tool. As you can see in this example, we're using a Chrome. The landing page of the core Tigo engine tool puts you in the first tab. In this 10-15 minutes example, we will go over the main functionalities the Tigo engine provides. First, we'll connect the hub, the bridge, and the master all together, and we'll see how the data is flowing into the Tigo engine. Then we'll go over a few more other features, advanced features used for configuration and wireless statistics. In this main tab, we're adding the wireless master, connecting the 2TH master into our Tigo engine software. On the right, top right, you can see connect a master. You can choose whatever name you wish when connecting. In this example, we will call the 2TH master. The type is 2TH, and the IP is provided as a label on the 2TH master. By default, all the 2TH configured with the IP of 192.168.1, and the three last digits are on the labeling of the 2TH. Once connected, you will see on the left the green mark validating the connection. The second tab shows you the master configuration. Out of the box, when we ship the 2TH masters, all the parameters will be set to functional mode. There is no need actually to configure those numbers. For advanced user, there's more on the user guide. The main working tab is the port configuration tab. In this one, we will connect and demonstrate the connection of the two bridges. First, we'll connect the vibration sensor, and then we'll connect the hub. As you can see, you can scroll down, and there are 16 ports available on this one. The 2TH master has a 2-track radio. Each track can support 8 ports. Once connected, we will be able to see the data flowing, the process data, at the checkbox PD-in. On the right, there are 2 tabs, the Scan tab and the Port Details tab. We will start with scanning and looking for the devices. The UID for the bridges are again labeled on the bridge. The bridge which is connected to the vibration sensor, where we can locate and find that and push pair. A menu with multiple parameters will be available pairing to the device. Tigo Engine user guides explains and details all the functionality for the parameters, but by default, most of the parameters are pre-configured for the functional mode. You will not need to change. The 2 key parameters you will need to know are the slot type, is it single or double? It depends on the amount of data you want to send from the sensors, and the retry field, which affects the latency, how much cycles will be used. The UID is already configured when you chose the bridge, and by pushing pair, you can see on the left going into operate mode. We are now connected and ready to go with the vibration sensor connected to the bridge. Let's scan also for the second one and find the hub. We will need to push scan again and find the UID for the second bridge connected to the hub. Once you locate this bridge, again, push pair and put it in the correct port that you wish. In this example, we're connecting it into port 3. Again, the list of parameters for the link, and again, choosing the double slot. The double slot is used because those vibration and hub are sending big amount of information. So we're giving them more slots. We're up and running with the 2 bridges now. One connected to the vibration sensor and the second to the hub. Let's go over to the port details. We are now looking at the port details of the vibration sensor. As we can see, the ports and the parameters for the bridges are already available. On the right, below the camera icon, there's a link to the IODD Finder. You can double-click that, and the IODD file for the specific sensor connected to the bridge will be downloaded. Let's see that's happening. So we download the IODD for the vibration sensor. As you can see, we already read some of the key parameters, like vendor name and type. We can also read more parameters, and this is done by reading the details from the IODD parsed into the Tigo engine. The next tab in the port details will expose the parameters for the connection. Once connected, you will not need to change those parameters, but it's a good reference to have when looking for the port configuration. The data tab will allow you to do ISDU write and ISDU read. For example, we've read the vendor, the device type, and the vendor for the specific vibration sensor. By typing the index and the sub-index, you can do the same. There's an option to change from data to string, from hex. If we move it to string, you can actually read and see the same type as we've done in the main details tab. The last tab in the port details will be all the parameters, the key parameters from the IODD file that we've just downloaded from IODD Finder. This is now part of the database of the Tigo engine, and you can use it. The download is one-time action. After adding it to the database, you can scroll and see the parameters in this device configuration tab. Some of the parameters are read, some of the parameters are read and write or have options. This is all reflected in this tab. So we're done with the configuration and seeing all the parameters. Now let's see the process data that actually comes from the sensor. As you can see, when we check the PD-in box, we're starting to collect the process data coming from the sensor. In this case, we're looking at the 20 bytes coming from the vibration sensor. On the right, you can see some numbers that reflect the link quality. LQI is the link quality indication, or RSSI is the received signal strength, both indicating good link condition. We'll quickly go over the hub and see the same process, just downloading the parsing for the IODD. And again, we can see the hub and read parameters reflecting the vendor and the device type. And we're done. Everything is connected. We have all the parameters and the process data. We will use a few more minutes just to introduce a few more key features with the Tigo engine. The second tab after the port configuration is blacklisting. It's a feature defined by the IO-Link wireless standard. It allows us to configure which channel will be used for the connectivity. This is a configuration for the master. By default, all the channels of the 2.4 gigahertz bandwidth, which IO-Link wireless operates on, are enabled. In this example, we're just disabling some of those. This depends on your quality of environment. It's a nice feature to have when you have a noisy environment and you can decide which channels are operating. The one step to enable the blacklisting of channels is power cycling the master. It affects all the ports and all the configuration. You can see in the main port configuration tab an option to reset the master. And once power cycled, you can return to the blacklist tab and see that the first 10 channels in this example were disabled. The next very important feature that we want to introduce is the upgrade. Enabling software updates to our masters and to our bridges and the hardware components is a key for deployment. The first two items relate to updating the software for the master. The third one, FOTA, firmware over the air, enables us to update the bridges once a spec update or key or major feature is added. We will run this one time to see the functionality. In this example, we have the latest software running on the first port, which is the vibration sensor. We would like to update the bridge connected to the hub. So we choose port number 3. The software for update is provided by Tigo. And once you upload the software, there is a quick process of updating the bridge. This process may take up to 30 seconds, not more. And I would like to show you those steps to explain that the connectivity loss for this process is minimal. You will see that the device is in operate most of the time and goes into disconnect mode just for 1 or 2 seconds. The expectation once this process is done is to see the updated version and to match the one that we've loaded into the vibration sensor. You can quickly see the sensor going to non-operate mode, but coming back in operate mode, loaded with the new software and the updated software. You can also go back to the port configuration tab, look at the details, port details for the hub, and verify that we got the latest software up and running on our bridge. The next 2 tabs will demonstrate some wireless parameters and configuration that we are enabling through the Tigo Engine software. Now, this is for advanced user just trying to verify the link parameters. We will show quickly the test parameters and the statistic that we enable to evaluate the reliability and deterministic way that wireless IO link operates. Do note that those features for test and statistics are for testing mainly. So when you do that, you're not sending operational data, but testing the wireless functionality directly from the bridge to the master. We can enable a latency test or a pair packet error test. As you can see, when this mode is enabled, you can choose which link you want to test. Is it the vibration sensor on port 1 or the hub on port 3? We will choose one example just to demonstrate this feature. When you run the test, you just choose the number of cycles that you want to run. In this short example, we'll do 10 cycles, and you can see that the cycle time is presented. This represents the round trip for a frame going from the bridge to the master and back, and the overall system for the wireless itself. We can also do a pair test packet error to demonstrate the reliability of the link. What we do in this test is run multiple frames as defined by the user, and count the numbers of frames we got in that sequence. The expectation is to be with 0 frames error. As demonstrated in this sequence. There is a PD in test and PD out test. Data coming from the bridge to the master or data sent from master to the bridge. You can choose each one of those and see when the test is done, the number of frames, PD in or PD out. The last tab, testing wireless functionality, is the statistic tab. This helps us test and see which channels are clean and demonstrate reliable link quality. This will help us to choose which channels we want to blacklist or avoid using the wireless functionality. As you can see, as we disable the first 10 channels, when we start scanning for across the channels, we start from channel 11 all the way down to the last available channel. And when scanning, we can actually see the packet error rate or per cycle or per subcycle. These numbers are expected to be very low, but in some sequence, if you can have a noisy environment and you want to avoid that, you can use that and go back to the blacklist tab and disable those channels and improve the link quality. The last one is the library or repository for the IODD files that we've loaded. In this example, we've demonstrated the vibration sensor and the hub. Both of those IODD that we downloaded for IODD Finder can be located here, and you can view some of the parameters. This concludes the main features demonstrated by the Tigo engine. And as stated, you will most likely use the port configuration tab as your main working tab, connecting the devices, pairing and unpairing, and also scanning and seeing the process data. The last section we wanted to demonstrate is connecting to a PLC. As stated, the Tigo Master can be connected either to the Tigo engine software configuration or to the PLC, where you can work over Profinet or Ethernet IP, and you can use different types of configuration software tools. In this example, we will use a Siemens PLC and demonstrate via TIO Portal the connectivity of the master and a bridge into the PLC. Let's see that happening. This is the main landing tab of the TIO Portal. Again, choosing a Siemens PLC for this demonstration. The PLC is already defined in this library. We need to upload the GSD file provided by Tigo. The GSD file, also EDS file for Ethernet IP software, will be downloaded part of the package and the kit. Once we download the GDML file, you can now find the Netfield wireless, which is our master, the 2TH master. We will now connect the PLC with the master. The one step to verify is that both are defined with the same IP. So the first step, we will configure the PLC to have the IP. We will connect the PLC with the 2TH master and verify both in the same subnet. The default configuration for the 2TH master, as stated, is on the label. When connecting to a PLC, TIO Portal detects the Profinet name, Netfield Wireless, and the IP can be changed, can be configured to use in your own subnet. In this example, we're using 100 for the PLC and 200 for the master, the 2TH master. As you can see here, 192.168.1.200. During this step, we're reconfiguring the IP for the 2TH master to now be used in your subnet. This is a quick monitoring tool just to verify that the two entities in our subnet are the PLC and the 2TH master. The one last step is to define the port. As stated, we will connect one vibration sensor on port 1. So we choose the port. You can see on the left, the PLC, the 2TH master configuration, and the port details for this one. What you can see also is the data. Where is the data is expected to come, the process data. We will see that later on live with the process data coming from the sensor. After defining the port, we will see a very familiar now, after doing that on the Tigo engine, a list of parameters. Unlike the Tigo engine, not all are configured, and the user needs to define the key parameters, which are all well documented. The key parameters that we care about connecting to the PLC is the UID of the bridge. Again, we have a bridge connected to the vibration sensor, and we want to use the same configuration like we demonstrated with the Tigo engine. These are now disconnected, and we're trying to connect the bridge and the vibration sensor to this PLC and the master. The key parameters to care about, as stated before, are the numbers of retries and the slot type, if it's single or double, making sure that on the double configuration, we can send up to 14 bytes of data per cycle versus a single, which can also only send 1 byte. Last is the UID for the device. We've seen that on the Tigo engine, selected automatically when we scan. On the TIA portal, we will need to enter the UID. On TIA portal configuration, it's inserted LSB to MSB. Once we do that, we're done. All we need is to compile our configuration, our definition, and we will need to download this configuration into the PLC. When this stage is complete, we expect to see the 2TH master already connected and activated, and also the bridge connected and activated, as we already defined the bridge, the UID, and the port configuration. So let's go online. You can see on the left, status is going into active mode. And you can see also the port details, an active green indication, showing that the connectivity from the PLC to the 2TH master and the bridge demonstrated. Last, we want to see the process data. Same way we've checked the box on the PDE in the Tigo engine. Now we need to define the actual fields that we want to monitor. Using the tags, we will define the first 2 bytes and see the process data coming. Again, we will need to go online and define the watch list, the tags that we defined to see the data. Once online, you should go to the watch tables and monitor the data coming from the sensor, vibration sensor, through the master into the PLC. In our example, we've put the tags for the 2 lower bytes of the data. You can see the monitor value in the orange column. And if we play with the sensor, vibration sensor, we should see the data coming in. We're all done. It's connected. So guys, thank you very much for the time we spent here to see all the components coming in together. The bridge, the hub, the 2TH Tigo master connected both to Tigo engine software and to the PLC. I hope this is helpful for you guys and that we'll be able to support you in the future. I'm waiting for Amit for some more use cases and usage with our components. Thank you.
Hey, thank you very much, Daniel. That was very educational. I feel that we have good overview of the Tigo engine, and I would like to say that if you have any question, please use the chat. We've got a bunch of questions. We're going to answer a few of them, but that's the time to list more of them. And if we don't have time, we're going to get back to you. So let's move on to talk about two selected case studies. So the first one I want to show, and I'll do it quickly so we have time for the chat, is IO-Link wireless for cobots and robots end effectors. Cobots and robots using intelligent end effectors, such as an IO-Link gripper, machine vision, or vacuum pump, will require a communication cable to the end effector. IO-Link wireless removes the need for cable. This adapter has an embedded IO-Link wireless device module in it. Just like this printed circuit board module that you can see here, the power to the adapter is provided directly from the robot's end of arm using the snip ring. The data between the gripper and the robot's controller is communicated via an IO-Link wireless master. So the master supports an industrial Ethernet to connect to the PLC. In this video from SPS 2019, when physical exhibitions will still exist and it was a real thing, you can see the IO-Link gripper that used to have cables on it to connect the collaborative robot with the end effector, now with no cables running along the arm of the robot. So basically you can see the robot's arm can do 360s, 720s, and completely have no limitations on the flexibility and the movement of the cobot. Moreover, it reduced the deployment complexity of this cobot. So wireless gripper provides full flexibility and enables complexity reduction with a cost-effective solution. The wireless communication enables low latency, reliability, and ease of deployment. The second case study I want to show you is IO-Link wireless for transport track and linear track systems. These transport track systems are a key element in the design of new machines in a variety of industries, such as consumer packaged goods, food and beverage, and automotive. The independent movers on the tracks are limited. The movers are not completely smart, and they lack the ability to have communication for real-time control and monitoring. For example, controlling grippers, vacuum pumps, and even load cells that are placed on the movers to automatically adjust the different sizes, shapes, and weight of products while in motion. This is simply not feasible to achieve with cables on these fast-moving transport systems that typically move at 2 to even 4 meters per second. In the same manner that power needs to be provided to the movers on the transport track through inductive power without any contact, then same has to be done with communication to the devices, and it has to be done without any contact to the movers. So IO-Link wireless provides the perfect solution here with a low latency, scalability to support hundreds of devices on the movers in a single machine area, and cable grade reliability, of course. By adding IO-Link wireless communication on each mover, the movers can now be equipped with vacuum pump, gripper, load cell, and other predictive maintenance systems directly on them without any additional external robotics or equipment needed. Such a solution enables products to be processed while in constant motion in the most agile and synchronized manner. So less mechanical components are needed outside the movers, which reduce the machine footprint and maintenance. It reduces and even eliminates changeover and tuning setup due to the fact that the device's configuration can be changed over the air from the PLC itself. So that's about it regarding the workshop. We received plenty of questions. Thank you everybody for the questions. And I think we're gonna tackle 2 or 3 questions in a few seconds. Let me grab the questions and see what we're gonna check on that.
Okay, Amit, thank you. There are some questions here. First one is, Amit, what is the maximum distance allowed between an IO-Link wireless master and the Tigo bridges, and how many Tigo bridges can you manage with one master?
Okay, so I hope that you heard the question. I'm going to repeat it quickly. So the question is, what's the maximum distance between a master and a device, and how many devices can be supported in each master? And that's a good question. So let's say by the protocol, IO-Link Wireless declares 20 meters radius from a master to a device for control and low latency applications. However, if we want to talk about monitoring applications, when it's not a mission critical application, then the range can be increased to dozens of meters. Regarding the amount of devices that can be connected to a master, so currently the Tigo Master 2TH supports 16 devices, but the IO-Link Wireless protocol declares 40 devices connected to each master. Yeah, I think that's about it for the question.
Another question here for Daniel. Daniel, the reset master you mentioned, is that a reset or a reboot? Meaning, are the settings to the original values kept?
So that's also a very good note from the crowd. The settings are set, so you're correct. A reboot is the right naming for that sequence. When you do reboot, you do not change any configuration of the master, and that's what's happening when we power cycle that. Thank you for the question.
Okay, Daniel, another question for you. So you were showing configuration of sensors with IO-Link Wireless. How can I control with the TigoStarter kit the actuators?
So we're focused on this session on the sensors, indeed. Similar to configuring IO-Link devices, you can also do actuators through the PLC. So you can use the tools provided by the PLC and connect and change any sensor or actuator. So it's not limited to sensors only.
Okay, thank you, Daniel. And Amit, perhaps last question for you. How much speed of moving devices would it be reliable for IO-Link Wireless communication? The speed that can be connected of moving devices.
Okay, so thank you very much. Yeah, that will be the last question for today. So the speed that can be supported, we are actually, we installed applications on a moving transport track systems, and these shuttles are moving at 4 meters per second. So I can say confidentially that it works over there. And on top of that, we have rotational speed. So on CNC machines where installed Tigo Air modules, we have 6,000 RPMs of these chucks that rotates inside this CNC machine. So basically, at the moment, we don't see any limitations on the speed of the IO-Link Wireless components, but we'll be happy to be challenged by you. So let us know if you have any interesting application. All right, so thank you very much, everybody, for joining. Thank you very much for your time. We appreciate your attendance, and we look forward to answer all your remaining questions on emails. So please, you can still share your questions on the chat, and I'm sorry to not getting to all the questions at once. Have a great day and stay safe. Bye-bye.